As our Honorable President, Professor Yadav, told that we hold a convention every year. And as this is a very mega event, under his leadership, we have decided we'll allot this convention prior to 2 years before the date actually convention will held. So like this, last year we decided it will be held at Graphic Era deemed to be university at Dehradun. So the professors came, Professor Joshi and Professor Ahmed, I call both of them, please come on the dais. And they would like to invite all of you to take part next session of annual convention of chemists. So there is a small video presentation and release of their first announcement. So please come so they can say a few words about the next convention and then we'll play the video.
Good afternoon to everyone, respected chief guests, distinguished dignitaries, eminent scientists, academicians, industry experts, scholars, and ladies and gentlemen. It gives my pleasure and honor to welcome you all to the proposed 63rd Annual Convention of Chemists 2026, jointly organized with the International Conference on Advanced Chemical Science and Sustainable Technology, to be hosted at Graphic Era deemed to be University at Dehradun, Uttarakhand. Before that, Graphic Era Group of Institutions was established in 1993 and now in 2008 converted into Graphic Era deemed to be University and 40th rank, overall rank in the category of university by NIRF. And thank you everyone for the 60th Third Annual Convention Chemist. Thank you.
So I request to play the videos. Thank you very much. So now I request our President, sir, to release the brochure of 23rd Annual Convention of Chemists. I request Principal, Sir Paul Whitson, please join this ceremony. Okay. चलो हम दोनों एक पता लेते हैं.
Thank you so much, Vijit sir, and best wishes to ICS for the upcoming annual convention of chemists. Now we will move on to the main part of technical session 1. We have plenary lectures. We are privileged to have Professor G.D. Yadav, President of ICS, who will be chairing the session now. To introduce our chairperson, I invite Dr. E. Rajkumar, Organizing Secretary of the conference and Secretary ICS TN branch.
Good afternoon, everyone. So it is my great privilege to extend a warm welcome to our distinguished President today, Professor G.D. Yadav, a visionary academic leader, an internationally acclaimed chemical engineer, and the Reverend President of the Indian Chemical Society. Professor Yadav stands as one of the India's most accomplished scholar, recognized globally for his profound contribution in science, technology, innovation, and policy. He is an emeritus professor of eminence and a former founding vice chancellor of the ICT, Institute of Chemical Technology, Mumbai. His extraordinary standing is highlighted by the fact he is one of the only 23 living Indians elected to the US National Academy of Engineering and the second Indian elected to the US National Academy of Inventors. Professor Yadav research has been instrumental in advancing the frontiers of green chemistry and engineering with a focus on sustainable and clean technologies. His pioneering work spans including nanocatalysis, biocatalysis. Many of his technologies have been successfully adopted by the industry, demonstrating his powerful commitment to translating the scientific research into the societal impact. His prolific output includes over 570 research papers and more than 140 patents. Furthermore, he has mentored a record number of students, giving over 120 PhD scholars. Yadav sir excellence has been recognized with over 150 rare and distinguished awards throughout the world. Most notably, he was conferred Padma Shri by the President of India in 2006, and the last year he was the Bhatnagar awardee, and for his exemplary contribution to the science and engineering. He is also consistently ranked as the #1 scientist in the physical chemistry. As the President of the Indian Chemical Society, Professor Yadav continues to provide a strategic leadership and vision for a sustainable bio-based economy. His career truly embodies the spirit of innovation, dedication, and transformative leadership. So we are deeply honored to have you among us today. Please join us with us to giving a warm welcome to Dr. G.D. Yadav sir.
Good afternoon, ladies and gentlemen. A few minutes ago, we inaugurated the next year's conference, 63rd ACC, that will be in Dehradun. I have been there, and I told the Vice Chancellor, you should hold this conference, and he readily agreed. Fantastic facilities they have, and you will enjoy it. And so Professor Narpinder Singh, who is a fellow of INSA, unfortunately, he's not here today, he's in Canada. But he said that he would do, and his colleagues have come here. So I'm very happy. So ladies and gentlemen, don't miss it. You will miss it. It is Dehradun, and beautiful place. So this particular lecture, this is the prime lecture of the Indian Chemical Society, Acharya P.C. Ray Memorial Lecture. This was instituted in the name of our founder, the founding president, Acharya P.C. Ray. And we choose this. I also want to tell you politely, none of the awardees knew that they are getting the award, because nobody had nominated them. So they were selected based on their scientific impact in international journals and their reputation in scientists. So I take great pride in that, because it is a recognition what they have done. And Professor Rawat is one of the best chemists who was earlier at University of Delhi, and currently he's the Vice Chancellor of Kumaun University in Nainital, where I had been very recently. He has done fantastic work in medicinal chemistry. From the Central Drug Research Institute, Lucknow, and he has built this. And I think his drug is now in phase 3, phase 2. His drug will be introduced. His drug is in phase 2. And he was also elected fellow of INSA. So that's a great thing. He has received numerous awards like CSR Young Scientist Award, ISCB Young Scientist Award, and now he's a fellow of INSA. And what is best about him? He has transformed Kumaun University, where I went there personally. He shares his bulletins with me. I'm very proud of you, Professor D.S. Rawat, and that is the reason we thought we should select a guy who has done fantastic work and can be a role model for the young chemists. So the floor is yours. Please come.
Thank you, Professor Yadav, for your kind word of introduction. And I am honored to receive this prestigious award, which has been instituted after the name of Father of Chemistry, Professor P.C. Ray. I'm humbled and honored. We all know about Professor Ray, but two things I would like to highlight here. One, that he wrote a book called Hindu Chemistry, which nowadays we even can't think of. And another thing, he said that science can wait for, but not this for us. And that he translated his in action later on. In 1924, when he established Indian Chemical Society and the Journal of Indian Chemical Society, before that he published largely on European journals. But after establishing this journal, he published about 60 to 63 papers, and out of which 51 papers were in Indian Journal of Chemical Society. And unfortunately, the journal lost its glory over the period of decades afterwards. But I'm so happy that under the leadership of Professor Yadav, the Chemical Society Journal has gained its own relevance now. And I think this is the only Indian journal which has impact factor of 3.4 at the moment. We must compliment Professor Yadav, and in less than 24 hours, he could generate 20 lakh rupees, and we all must learn from him and how we can do something like this. With this, let me just show you. I come from University of Delhi, and that's the building what we call Viceroy Regal Lodge. It was constructed in 1902, and Viceroy of India used to operate from this building till 1933, and in 1933 they moved to Raisina Hill, and this building was given to University of Delhi. And this building has historical importance because Bhagat Singh was kept underneath of one of the underground room this building has. Gandhi-Irwin Pact was signed from this building. And the registrar room, there is a stone carved and written that Mountbatten proposed Lady Mountbatten in that particular room, which is occupied by the registrar of the university now. So that's this part is the central block of the chemistry department. This used to be the kitchen of the then Viceroy, and my lab office is located to this side, and lab is underneath of this. So in 2023, I joined Kumaun University, my alma mater, as a Vice Chancellor. And this is the administrative block. We have 2 campuses and 10 faculties, more than 70,000 students. And you can see it's a lush green area. And my accommodation is to the top corner of this, which is about 100 meters from this place. And I'm strictly warned not to come out on the odd hours because we have very good companions around. So this is the lake city called Nainital. Those who have not visited, this is the place one must visit. And this is the main campus, what we call the DSB campus, and that's the area where my office is located, which is about 2 kilometers away. And another campus is located in a nearby town, small town called Bhimtal. So that's another campus what we have, which is 1 hour drive from Nainital. And it's cold place. At times it snows heavily, so it looks like this. So after joining the university, I thought, let's do something different. So I decided to go to the classroom and teach to the students. So I take classes at the DSB campus, 2-hour class per week. And this is the same classroom where I studied 30 years back. So in the same classroom, I'm taking class now. With this, let me just give you the glimpses of the work, what we do at University of Delhi when we talk about drug discovery till the mid of 19th century. All kind of diseases, people used to rely on natural products. Okay, and the first written evidence of the uses of medicinal plants has been found in the Sumerian clay slab, which was found 5,000 years old in Nagpur. And it comprises 12 recipes for drug preparation, referring to about 250 various plants. But when it comes to synthetic medicinal chemistry starts with the discovery of urea by Wöhler in 1828. And first synthetic drug is termed to be the chloral hydrate, which was discovered in 1869. So from 1828 to till date, how much it impacted the human life, this slide shows you. At 1900, the average age at birth in India was about 23.5 years, which has gone up to now 66 years, largely because most of the diseases which were uncurable have the treatment available now. So when we talk about drug discovery, this is one of the slides every medicinal chemist will show you, because at the end, people should not ask you whether you discover any drug or not. It's very challenging. When a medicinal chemist synthesizes about 10,000 compounds, one compounds come to the market as a drug. It takes about 16 to 18 years, and the cost of the drug development is about 1 to 3 billion US dollars. The approaches by which we design the molecules that can have a biological importance, these are some of the approaches. What I'm going to talk to you today is about hybrid drug discovery. So if you look at this slide, most of you must have seen this plant. This plant called Sadabahar has been source of alkaloids. Not less than 120 alkaloids have been isolated from this plant. 70 odd alkaloids shows biological response. The structure of 2 such alkaloids are shown over here. Both of these alkaloids shows poor anti-cancer activity. Okay? But same plant generated 2 more molecules, something like this. This is called vincristine and vinblastine. Vincristine and vinblastine were licensed by US FDA in 1963 for the treatment of leukemia. So what this slide tells you, that if you have 2 molecules which are hooked up like this, you make a hybrid molecule, and these hybrid molecules have a better pharmacological effect than the molecules which are single pharmacophore. But synthetic medicinal chemists did not utilize this concept till 1997, when the first paper was published where people showed that kind of response. We started working at University of Delhi. So when I started my career from Naipur Mohali. When I joined Naipur Mohali, one day the director called me. He said that we have a thrust area on malaria. Why don't you work on malaria? Since I'm PhD from CDRI, I knew about malaria two things. One, this molecule, the top one, called artemisinin, for which the Chinese scientists got a Nobel Prize of 2015, artemisinin. The bottom structure is the chloroquine. This is the gold standard story because we all studied about it in our medicinal chemistry course. But if you want to work on chloroquine, nobody will fund it because it's a more than 100-year-old nucleus. And if you want to work on artemisinin, CDRI group works on this. So I thought to look for something different. I came across this molecule called tetraoxygen. First paper was published in 1999. We started our career in 2002. So we started thinking about this molecule and made some progress on it. But at the end, around 2008, we designed a hybrid molecule, something like this. The green part comes from chloroquine. The yellow part comes from these two antimalarials, made the hybrid molecules. What we showed is this. If you look at this slide, this is the hybrid of aminoquinoline and trigi. This is the IC50 value of chloroquine, and this is the IC50 value of our molecules. What we showed here, that some of these hybrids have much better anti-malarial activity than the standard drug chloroquine. So as a typical medicinal chemist, what we did now, we substituted this nitrogen by CH and made aminoquinoline pyrimidine-based hybrids. So I will not talk about this synthesis. So these two regioisomers, the purification is a little bit difficult. It takes 2 to 3 days to do the column chromatography to remove separate these two regioisomers. But the good part was, if you look at these two structures, the difference is point of attachment of this nitrogen with the pyrimidine ring. Both have similar kind of antimalarial activity. So this was a good news because if the lower yield product shows the activity, the life of the student becomes miserable. So we went ahead with the major compound. We converted it, some of the derivatives. What we showed here, that from 26 nanomolar, we ended up a molecule with 7 nanomolar. So whenever you have a nanomolar range molecule, two questions will be asked. One, what is the toxicity of the molecule? Another one, whether the biological response. So what we did actually, we did the in vivo activity. In this case, we showed that this molecule has a curative effect of 80%. The mice were treated. So no toxicity. And we published the result in ACS Medicinal Chemistry Letters. And by the way, we patented this molecule and then we did this publication. And when we published this paper, one fine morning, I received an email from Kwang Shu Kim from Harvard Medical School. He showed his interest to screen these molecules for Parkinson. So where is malaria and where is Parkinson? There is no correlation between these two diseases. Why this was? This was because there was a paper published by Sanders in Nature in 1987, which concludes that chloroquine and related molecules can retard the progression of Parkinson's disease, though there was no mechanism known at that time. He screened 960 FDA-approved drugs, got 3 hits. All these 3 hits has 4-aminoquinoline pharmacophore. So we started collaborating with him, how this Parkinson happens, how these molecules act actually. There is a receptor in our brain called NER1 receptor. Till 2015, there was a conception that NER1 receptor is the orphan receptor. So orphan receptors mean the receptor which does not have a binding pocket. But this study proved that no, it has a binding pocket, which is very tight. When a mystery molecule binds with this receptor, the receptor undergoes for activation. And when it activates, death of the dopamine neuron get arrested. And if your dopamine neuron death get arrested, you can have the better curative effect. There is no drug for the treatment of Parkinson. So to show you how this Parkinson happens, this is the normal brain cycle, you have a dopamine neuron, you have a dopamine here, alpha-synuclein protein looks like this. But if you have a Parkinson, the first thing is the dopamine neuron death takes place, you don't have a dopamine. So your movement problem starts. The second one is, this undergoes for misfolding, forms this kind of lumps. So what you can do now, if you want to work on Parkinson, either you stop the death of the dopamine neuron, or you stop the aggregation of alpha-synuclein. Based on this publication, the Journey with Parkinson in 2015 made a commentary and wrote, clearly there is a real potential for future application moving from the rat model of Parkinson's to one day testing clinically in humans. So we started this work. Initially, these two series of molecules were designed and tested. The trigen-based compounds were totally inactive. We got very poor activation by these four molecules. From there, our journey started, and we started making changes in the molecules, which is shown over here. Synthesized more than 700 compounds, multiple step synthesis, and this was funded by MJ Fox Fund in 2014. Now, if you look at the EC50 value of chloroquine, it's at 50 micromolar, and some of our compound EC50 value is as small as 0.5 nanomolar. This is in vitro data. Let me just show you how we got this SPB94 compound. This is for the students. Okay. So we published this work in Royal Society Advances in 2015, and my biology counterpart wanted this molecule in a higher scale, so they wanted to do more biology on it. While the student synthesizing this molecule, one fine evening he came to me. He said that in a 100 milligram scale, I got 8 milligram compound, which is more polar, and there is no structure. So I said, let's characterize it. We characterize it, and looks very interesting based on the receptor structure. We isolated it, did the testing. What we got now, the compound was 0.5 nanomolar active, and on this molecule, we got a nature communication. The next series of molecules were like this, and now we have molecule as active as 0.1 nanomolar, and we have 40 lead molecules from this series. What I talked to you today, till now, is all in vitro data. So let me go back again, a little bit talk about the biology, how it looks like. So what we are talking here, the activation of NER1, how much it is getting activated. So this slide shows the luciferase enzyme assay using NER1 ligand bind domain. So the green is the chloroquine, and red one is our compound. The chloroquine activates NER1 at 100 micromolar, our compound at 20 micromolar. Same result is due to this side. Now it is a ligand bind domain only. Same result were obtained. The bottom one is the red dots are the dopamine neuron. When this is treated with compound called MPP+, that causes a Parkinson, and LPS, Parkinson causing agent, what happens? The red dots depletes in both the cases. It means the dopamine neuron dies. So now when this is treated with chloroquine, you can see a little bit more red dot comes over here. But when this one is treated with our compound, you can see the red dots are there. So what this study showed, that induced death of dopamine neuron up to 60% of the healthy cell. But when this is treated with our compound, the 40% lesser concentration, our compound rescued the dopamine neuron. So when you rescue the dopamine neuron, your concentration in your brain of dopamine increases so that you don't have a Parkinson. So that has a curative effect. So this is in vivo data now, the real data. So what it did, this is the serotonin part of the mice. When the mice is injected with the compound that causes a Parkinson, this looks like this. When this is treated with L-DOPA, the compound which is given right now for the management, not for cure, to Parkinson, not same, not different, but when this is given to our compound, the first and the fourth looks same. So what we proved here, that this compound has curative effect. This is number one. Number two, the alpha-synuclein misfolding causes Parkinson. So what we did, this is the vacuum, and when alpha-synuclein is given, it looks like this. When this is treated with our compound, it looks like this. So what this molecule is doing? This molecule is doing two things actually. One, it stops the death of dopamine neuron. Number two, it stops the aggregation of Parkinson's disease. That's why it cures the Parkinson's disease. The third mechanism is more beautiful. Autophagy, I don't know whether students have heard about it or not. 2016 Nobel Prize was given to a Japanese professor on autophagy. In a common language, autophagy means that when you are fasting, your cells are under stress. To survive, the cells eats the cellular garbage, the cells that causes a disease. So that is called autophagy. What this molecule is doing, you have yellow dot and red dots. So when this is treated with this compound, yellow dots, red dots are gone. So autophagy stops. Now, when this is treated with chloroquine, 22% autophagy was dropped. Remember the structure of our compound and the chloroquine, almost same except the side chain. Now, when this is given, our compound, 64% autophagy was induced. So this molecule is doing three things. One, it stops the death of the dopamine neuron, it stops the aggregation of alpha-synuclein, and induced autophagy. So this got the US FDA approval in 2023, and first molecule from Indian academia to get the US FDA approval. And we published this work in Nature Communication. And in 2024, the phase 1 human clinical trial of this molecule was made available by these three pharma industries. What it says ATS-399A was well tolerated with no major site safety issues in any of the 76 participants. No serious treatment-related adverse events were reported, and such findings were proportional to between placebo and dosed group. PK result shows once a daily dosing. Remember in 2015, this is what it was speculated, that one day it may be used in the humans for clinical trials. We were lucky enough in 2024, we got these results. Now this molecule has moved to phase 2 clinical trials. And these are the students who made this story a success from 2012. And these last two students are currently working on this project. It is not one molecule actually. So this molecule has cleared the phase 1 now. These two molecules are preclinical stage of development. So we have two more molecules, one for dementia, another is for autoimmune disease, for which there is no drug. So this is the website of Hannongbua Biopharma, where they showed our compound as phase 1 clinical candidate. The story was published by Bloomberg, Wall Street Journals, all under international media on this work. And this is what ultimate happiness, that the group of scientists at Harvard University and University of Delhi discovered this molecule. This is the first molecule on this target which has entered to phase clinical trial. Couple of slides, 3 or 4 slides. After joining the Kumaun University, our system is full of uncertainties. When I joined Kumaun University, my university, Delhi University said, no, you can't have PhD student, you can't have a funding, you cannot have anything now, but you can keep everything, whatever you have here. So lab without students. So the students who are working right now, those who joined before I left, so some of the work. So this is actually, in this case, what we showed formation of this cis-phenyl sulfone using biphenyl phosphine oxide. And this reagent has never been used for the halogen atom transfer reaction. So we made this, it's very chemoselective, And we propose that this goes via radical mechanism, which we proved later on. And we could even isolate this compound, the iodide, this is the trans one. So when the free radical attacks, you get the cis-vinyl sulfone. And we proved that it is a radical because it was trapped by tempo. I will skip this slide. Yeah. Just this work just got accepted in organolators. So the carbon-carbon bond formation in the third position of oxyinol, this is one of the methods by which you pre-functionalize the third position and use the metal catalyst and make these compounds. The second one is you use something like this. This third position becomes a nucleophilic and make a carbon-carbon bond. Only aliphatic substrates were reported. And what we did in this case, we used iodine as a catalyst. And we got this transition state. When we get this, now this becomes the electrophilic site. Here is a nucleophilic site. So we could get the carbon-carbon bond formation reaction using aromatic substrates which are not known till date. It is just in press right now. The last one is, this is called quinine methyl. MSc students can write a resonating structure of something like this, which is deuteranic form. Utilizing deuteranic form of the quinine methyl, more than 1,500 papers have been published till now. When my students started discussing this to me, I said, there has to be this structure also, because as an MSc student, you can write this resonating structure as well. But there was no report which talks about the presence of the diradical intermediate. If that happens, in first case, the nucleophile attacks. If that happens, the electrophile attacks now. So what we did actually, it undergoes for dimerization. We could isolate the dimer, X-ray crystal structure, trapped by tempo. And when he was doing this, I said, can we do the low temperature EPR to detect the presence of the radical or not? Because biphenyl methyl radicals are not known. And to our surprise, this is room temperature stable. This black graph shows at 25 degrees centigrade, this biradical is stable. So what we can do with this now? With this, we can convert this to biphenyl or triphenylarenes, this molecule. A Br can be attached at this carbon, which was not possible before. If you react this with electron withdrawing group, you can get the cis alkenes. This cis alkene on addition of HCl at 80 degrees centigrade gives you this kind of cyclized product, de-aromatization of the pyridine, which generally requires the metal. This iodovinyl sulfone gives this kind of compound. You can introduce the chirality in this molecule. Terminal alkyne gives these kinds of fluxones, which can be used as a ligand for carbon-carbon bond formation reaction. And finally, you can convert this to this kind of triaryl ethanes. Why this is important? Because the cost of one of the molecule listed here is 50 milligram, cost about 16,000 rupees. So with this, we work a little bit on green chemistry also. So this is what we have published in this area. With this, I acknowledge the malaria work was collaborated with Professor Shabana Khan, and the work on Parkinson was with Kwang Shu Kim, and funding came from all these CSIR, DST, PERS, and all these grants. And these are the students who made me what I am today, very dedicated people, and most of them are well settled now, and this is the current batch of students. By that time, I think I will come back, most of the people will pass out, so my lab will be again empty. So thank you very much for your patience here.
Thank you very much, Professor Rawat. I want to tell you something. Acharya P.C. Ray worked on chloroquine, and that is how he started his Bengal Chemicals and Pharmaceuticals, and also the so-called ICC now, Indian Chemical Manufacturers Association, was established in 1938 by him. So he's the first startup company owner in India. Right now we talk of startup, but he had done it. Not only that, he was the first Indian to use ionic liquids. So fantastic work, kudos to you. So Acharya P.C. Ray and his legacy. Thank you, Professor. The award will be given to you in the evening, not now. Okay.
Now felicitation. You have a felicitation.
Okay, felicitation. Yeah.
Now Professor G.D. Yadav will felicitate Rawat sir with the memento and the ICS compliments.
Now, my proud privilege is to invite Professor G.U. Kulkarni. He will give Acharya J.C. Ghosh Memorial Lecture. G.U., I have to get some money for this award also. I have known him since his PhD days in IISc Bangalore. One of my PhD students worked with him in his lab, in CNR's lab. So I have known him. GU is a fantastic chemist, solid state and structural chemistry from IISc Bangalore in 1992, followed by postdoctoral research at IISc and Cardiff University. So he has held visiting positions in Tokyo University, University of Bayreuth in Germany, and also to his credit, there are some adjunct professors positions. He has authored 340 papers, 17 book chapters, and holds 28 papers. And he has received numerous awards, including Sadborough Medal for his PhD thesis, B.M. Birla Science Prize in this Material Research Society Fellowship, and he's a fellow of all Indian academies, particularly INSA. I know him for a number of years. You have been a fantastic chemist, so please inspire our audience.
Good afternoon. It's an honor to be a recipient of the Acharya J.C. Ghosh Award. Sir J.C. Ghosh was an eminent chemist in the country. He contributed immensely to photocatalysis, reaction kinetics, in many other areas. Around 1940s and 50s, held many eminent positions, including, I think, just then the IIT Kharagpur, in some other name, it got started, and he was the director of that. He was also the director of the Indian Institute of Science, my alma mater. So it's truly an honor. I'm moved by this. I'm humbled by this. Thanks to my all students and collaborators who have contributed to whatever I have done. And thanks to the jury, thanks to President Professor Yadav. I didn't know about this. I mean, I knew about the awards being given by Chemical Society, but I had no clue that I would be getting for this year. And the surprise, there was an email from him sometime in October. I was so pleased to see that email, and today I'm here to talk to you. I have chosen to speak one of the research areas, what we practice in the group, that is to do with the gold. Gold, I don't have to introduce much, the ring itself. I'm here for the next 20-25 minutes to, don't disturb Yadavji, please, he has to listen to my talk. It's on gold. I'm here to impress upon you that whatever gold you are wearing or you may be possessing, it is not really worth it. You have to be buying gold from me, okay? So that's all thanks to all the chemistry knowledge we have gained over the decades, particularly under the mentorship of Professor C.N. Rao and other very encouraging personalities like Professor Yadav. As he mentioned, he has been mentoring me from my PhD days. Thank you very much. How do I do it? I mean, I can go to the board and do, or I can do from here. All right. So we are talking about gold along with other metals to begin with. Gold crystallizes in face-centered cubic structures. This is all we have learned it in our college days. And in fact, metals themselves, if you just scan across the periodic table, metals actually like to get into very close packed structures, either cubic, particularly face-centered cubic, or hexagonal close packed structures. We teach this in the class because they're all close packed structures. Each atom is surrounded by 12 atoms in FCC, and the packing fractions are listed out there, along with the coordination numbers. And that is all because of the metallic bond. We have itinerant electrons which are moving around, contributing to the metallic bond. They also ensure that the metals remain in high-packed symmetric structures. There are a couple of metals which go to hexagonal, like the ones listed out here, zinc, cadmium, etc. But most of the metals get to FCC. All the familiar metals, what we use day in, day out, they are all FCC metals. And they like to be so in spite of extreme conditions. You can imagine you take a piece of metal and heat it and put some pressure on that. Does it undergo phase transformation to some other crystal structure? You look at it, one would require, if you take silver of the order of 92 gigapascal, it's a high pressure actually, quite a high pressure. And it can transform itself to other type of crystal structures like trigonal, hexagonal phases. And you can look at the other metals, copper also does, palladium also does, but platinum and gold, they would require to the tune of few hundred gigapascals. And platinum does undergo phase transition. Gold undergoes phase transition only momentarily. So robust is the structure. I can show you, if you're familiar with X-ray diffractogram data, this is the familiar FCC diffraction pattern. The Bragg reflections 111 and 002. I want you to remember this as we go through the presentation. And in spite of applying around 250 gigapascal and heating to around 500 degrees centigrade, you can see that gold remains as it is, except for small features coming up. They pertain to hexagonal phases. You think you have made gold in a different form, but the moment you cool it down to room temperature and withdraw the pressure, it happily comes back to face-centered cubic structure. Extremely robust. No one in the world has made any other type of lattice structure of gold except us. Okay? So I'm going to show you some exciting results. Hold on. So gold is very, very robust. But when it comes to nanoscale, the story is somewhat different. If you make gold anything smaller than 1 nanometer, under the electron microscope, you apply tiny pressure, it undergoes phase transformation more readily. At reduced pressures, you don't need 300 gigapascal, 1 or 2 gigapascals will do. You are working with a very, very tiny lattice. But the moment you remove the pressure, it goes back to, again, FCC, even at such small structures. We reviewed the literature on various types of crystal structures exhibited by metals, including those of the noble metals, etc. And the summary slide is here. Where do you find gold? You see here, this is FCC, but it doesn't take up anything other than being in a nano. These are all our literature, okay? This is all ours. So what I mean to say is, gold is robust. In spite of being nano also, it is robust. When it comes to bulk crystals, you just can't speak of it. Even if you apply a few hundred gigapascal higher temperature, it undergoes phase transformation only momentarily, unlike other metals. Let's begin with the nuclei which lead to the given crystal structures. If you start out, for example, chemically, it doesn't matter how you start out making the nuclei, they can go into these tiny, tiny nuclei like this. These are all this is where the birth of cube is, cuboctahedral structures. I don't have much time to get into the details, but the faceting is different. You can see there. The other type is multiply twin structures where we have five-fold symmetry, and these are decahedral structures. Decahedral structures. And for the first time, we made big crystals of these nuclei. If you allow them to grow, they actually grow into different shapes, starting from these nuclei. But in the lab, we made perfect cuboctahedron, where you can identify the facets looking at the geometry. Anyone who has studied elementary X-ray diffraction will readily identify that these triangles are 1, 1, 1 facets, squarish ones are 1, 0, 0. That's the cuboctahedron. And it's a perfect FCC structure. When it comes to decahedron, it's all decorated with 1, 1, 1s with the twin planes here along the boundaries. I'll get into that in a while. Now, if you look at silver, it actually, when you make silver into different type of nano forms, particularly nanowires, these are commercially available. You can buy a drum of dispersion of silver nanowires. People use it in electronics. And these readily host these kind of pentagonal tips, and they're hosting a lot of non-FCC phase, okay, along with the 100 type of facet there. And we should realize there is an angular symmetry disorder already built up, because you can't take FCC structure and build on only 111s. So the tip being made up of only 111s, it leaves some angular gap there, and that's the reason all the interfaces are strained. And you can see the traces of them in the X-ray diffractogram. This is from the literature. You can see little asymmetric peaks coming up like this, and people have assigned them to be some foreign lattice, like body-centered tetragonal phase, unlike the regular FCC phase. So, other than gold, there are plenty of examples in the literature wherein you can find deviations from the parent lattice, like the FCC. Okay? But the same is not true with gold. We started out working with lots of chemical aspects of organic complex, organic media hosting metal complexes, particularly phase transfer from the aqueous media. We were doing nanochemistry with them. And soon we realized that if you take AuCl4- ion and phase transfer it using regular phase transfer reagent like tetraoctyl ammonium bromide and hold it in toluene kind of organic medium, you can do wonderful nanochemistry with it. This is a known procedure in the literature. What is not known is you can actually thermalize this particular complex and readily make single crystals of gold. What kind of single crystals? They're all FCC. See, for example, this is a microplate. It's a very simple process. You have this organic concoction and put it on a hot plate around 130 degrees centigrade. That is the thermolysis temperature, and hold it for many, many hours, because you want the reaction to go very, very slowly so that you will have defect-free crystals getting formed. And you can make millimeter size microcrystals, which are all gold single crystals. Look at the proliferation of 111 here. This 111 is the one which is hosting least surface energy. I'll come to that in a minute. And they're perfectly flat, and you can use it for tunneling microscopy measurement, or you can use it for molecular electronics, so on and so forth. Many of those things we have demonstrated in the literature. And even when you pack 111 microcrystal, there is only a tiny bit of 100s along the sides, without which you cannot complete the structure. So only to a little extent, gold can tolerate 100, otherwise it mostly is hosting 111s because that is the surface with least surface energy. But when it comes to this family of structures, decahedral structures, you can see here the twinning which is along this interface, that's the one which is going to dominate if you want to make them grow bigger and bigger. And at that interface, there's a likelihood of strain in the lattice and likelihood of inducing phase transition in the gold lattice itself. So what we did was, we really wanted to confuse gold crystallization. So we brought in Ag+. In fact, we were also keen to make some, alloy plasmonic systems. You take silver and gold, whether it exhibits different type of surface plasmons we are looking at. But to our surprise, we landed somewhere else. So this is Ag+ getting mixed up. Similar complex is being made to certain ratio, in certain ratio. And again, hot plate experiment is very, very simple experiment in air. And what silver plus does is something wonderful. It doesn't form alloy. It doesn't mix with gold at all because it has Br minus next to it, and that is pulling it out. But it does confuse gold reduction going into FCC. It confuses that path and pushes it into another type of lattice. So it actually encourages the formation of these kind of pentagons, which can be actually made to grow into bigger structures like the bipyramids. And so we have a mixed complex now, AUAG, and taken through thermolysis. And you can see the different stages of growth. This is a nucleus to begin with, the gold nucleus, and it is made to grow bigger and bigger. It actually forms this kind of bipyramidal structure with narrow tips. And I can show you more of microscopy. You can see that the tips are made up of 111 pyramids there in the end. So this is a corrugated structure. You can imagine that you have decahedras. You have initially one decahedra formation and another decahedra. It is actually wanting to grow, but it is unable to grow because of the lattice strain. It encourages the growth of another decahedron, but that also cannot pack itself. It has to get a little twisted. So that's how the growth of the bipyramid takes place. We have thoroughly modeled it, and all the results are in the literature, but this is the essence of it. What we need to understand is there is corrugated structure like this, very interesting structure, not seen before, and take it from me, it is hosting a lot of lattice strain. It is hosting it because it is striving hard to still remain in FCC. In spite of all this, it is still in FCC. What we can do further with it? We can actually control the kinetics. If we accelerate the kinetics, is there a possibility that we can induce more strain? In physics, it matters. If you induce more and more strain, what happens is you will actually induce the phase transition itself. So whether that would be a possibility. So we looked at varying kinetics and all. Finally, we arrived at a particular condition in which we could actually make lots of these, what we call as gold rice particles, either in FCC or in non-FCC structures. Proof is here. For the first time, I'm showing you gold getting into non-FCC. This is a familiar FCC, 111002. And if you look at these peaks now, red curve, a lot of foreign lattice has come through. This is the 002. And it took us 6 months to figure out what kind of space group would fit in, what kind of unit cell, how is the supercell relation to the parent lattice, how atoms had to move to release a bit of strain to get into foreign lattice. All that, it took us time, but nevertheless we fixed it. And finally what we learned is it's a mixture of the body-centered tetragonal and body-centered orthorhombic phases of gold, which didn't exist in the literature. For the first time we introduced them. And yeah, that's a supercell relation and all. Again, I cannot get in through the technical details. The question is, how is this strain distributed across the crystallite? Whether you take the FCC bipyramidal rice structure or the one which has undergone the phase transition to become orthorhombic and tetragonal, how exactly the strain is distributed? And you cannot take the sample under a normal diffractometer and try to find it out because it will give an average information. What would be ideal is to take one crystal and look at, these are two tiny crystals. And if you want to look at the strain distribution, you have to have your beam much, much smaller than the dimension of the particle itself. So we went to synchrotron at Petra Desi near Hamburg, and this is a synchrotron beam. And I must announce something to students particularly, that on behalf of Department of Science and Technology, DST, JNCASR, my institution, is coordinating visits by scientists and students to couple of synchrotron beam lines in, globally, in Japan, in Germany. So the information is on the web. A lot of people, there are 1,000 users in India. They all apply, and there's a review process at Germany, and also there's a panel committee set up by DST. They all go through. What we do is to sign check for you to go. That's all we are doing. But rest assured, I can tell you, we process it at very fast rate. So many people have made use of it. It is still on, and I urge students to make use of. This is my student Chetali, who is a beam scientist there. And in one of the studies, what we did is to scatter some crystals and actually choose one among them with a lot of difficulty. This is the crystal, and look at the crystallographic phases existing in this particular crystalline. And this is how the experimental arrangement is. And there are many things one has to be observant here. After all, in such a big system, you're working on a crystallite which is hardly about 1-2 micron length and half a micron width. And so you have to know that your nano beam is after all just about 50 by 50 nanometer wide. It's focused onto the crystal and goes in a raster fashion. Of course, we had a lot of help from German scientists working there. And that's how the data gets collected. So from each spot, you'll be getting diffracted beam coming out, and you actually go on mapping the kind of phases existing in the crystal. The summary is here. As you move the beam, you can see, I'll just read out the summary lines because there's no time for rest of the details. Crystal planes are 6 degrees twisted along the length. I said when the decahedral structures nuclei pack up, there is a twist of around 6 degrees along the length. Okay, that is one origin of the strain itself. And there are a lot of mirror reflections present because on either side of the bipyramid, you have mirror planes working. You can actually translate from one to another through symmetry structures. And a lot of twin boundaries exist, and we get all the signature of them. And what we learned from this study is there's a co-presence of face-centered cubic and body-centered orthogonal structures, and they exist in core shell. Core, the thick of the core, 90% of the crystallite is made up of orthogonal structure, orthorhombic structure, and only the skin of it and the tip, both tips are made up of strained FCC. Okay, this is what the lesson we learned. And we have done many more studies on the synchrotron beamline, including taking a given crystal and heating it to high temperature. What temperature it takes for getting back to its parent lattice, that is the cubic structure. We have to go all the way to 800 degrees centigrade to put it back to. So whatever we make non-FCC, it is not that we make it, next day it comes back to its native lattice. It's not that. We make it and it stays. It stays for a number of years as we have checked. Optical properties, there is not much surprise. If you have worked on anisotropic rod structures, whatever the longitudinal or transverse plasmons, we just see similar scattering coming from these plasmons, absorption coming from these plasmons. We have done a careful study to look at the absorption property. To naked eye, if you take our gold and compare it with ordinary gold is sort of yellowish in tinge, but ours is orangish, slightly different type of color it exhibits. Well, there are different correlations and all that. Chemical stability. If you take the crystallite and put it in adsorbents like sodium sulfide, it's quite an aggressive adsorbent. It can readily phase transform provided you heat it to around 100 degrees centigrade. This is the non-FCC peak. This is the FCC peak, and you go on heating, this peak vanishes. Okay? So once the sulfur adsorbs, that can induce release of strain and phase transformation. What is most interesting, I'll tell you. This is the take-home message from my talk. In our high school lessons, we have learned gold is noble. It can stand aqua regia. Okay? The only thing it reacts to is mercury, for example. It forms an amalgam. So these are all the lessons we learn in high school, right? So we were keen to see how our unconventional gold behaves. So we had to bring on the platform both players, FCC and non-FCC, under given conditions, how things evolve. So if you look at amalgam formation, the top two cuboctahedrons are FCC, and this rice is basically non-FCC. And you treat it with mercury, you can see the trace of the cuboctahedron, but everything is gone away. But non-FCC rice stays. So it is non-reactive with respect to mercury. And we have done DFT calculations, modeled it, why, how, everything. But again, I don't have time to get into. Basically, you are essentially controlling the silver. The metallic radii are same, silver and gold. You are controlling its surface diffusion into the lattice. And that doesn't happen if you have anisotropic surface unit cell. This is what we showed with our calculations. Come to aqua regia. This is the FCC crystallite I had shown you in the earlier slides, and exposed to aqua regia. It's very clear. Our crystallites, which are non-cubic, do not interact at all, whereas this is eaten away, right? Aqua regia does interact with gold, but only the conventional gold, the FCC gold. Non-FCC gold is much more robust compared to gold. When this paper got published in Angawanda Chemi, it became news in various media and all that. The Indian company Tanishq approached me. Can you make gold for us? So we want to make jewelry out of it, which is much more robust and all that. We had lengthy discussions. They even sponsored an industry project and all that. But what I could show them was, I can make 1 milligram for you. Later on, you have to do the translation. Well, somewhere there the discussion stood, and we'll have to take it forward. So the take-home message is our gold is even more robust against the conventional corrosive agents. Yeah, I think I have almost come to the end. Okay, having realized the crystallography of our crystallite, if this is the crystallite, tips are made up of FCC, can I simply chop off the FCC part and retain only the non-FCC? I'm showing you here that possibility exists. You can actually take these crystallites and treat it gently and then rip off the FCC part. You are essentially left with only non-FCC phases here. Okay? So this also was shown to the company if you want to make only these. So these are many attractive features of the kind of gold we can. And there are a lot more chemistry is possible. Okay? So you can make other things which interact only with the FCC and with the non-FCC phases. For example, you can under potential deposition of platinum you can bring in. And so here the platinum deposition, and you can bring in other metals also. Copper you can bring in, right? So you can make some dumbbell shapes and all. They will have very interesting optical properties. If you are looking at plasmons and all, fantastic. I mean, they have very interesting properties. And I think, what? Time is there or no? I think lunchtime, so I better finish. I'll take another 2-3 minutes. You see, once you have realized a different type of lattice, you are actually sort of challenged. You want to see what it takes to get it back. Can I apply more and more pressure? Can I apply more and more temperature? Can I expose it to some ion irradiation? What it takes to get it back. So that establishes the energy landscape of whatever we have made. Okay? So there were a lot of academic studies in the last few years, like adsorbent I already showed you, sodium sulfide, and many more adsorbents we have tried out. Temperature we have studied in the lab and also with synchrotron, and applying pressure we have tried up to 40 gigapascal on Soleil synchrotron in France, and in the lab we have exposed to argon beam and looked at the phase transition. And there are very interesting stories there. This is the thermal stability done in the lab. So you can see now this gold is absolutely stable even at 500. You can see that the foreign peak. This is where we need to have the peak for pure FCC. And only above 600, 700, you see that the foreign lattice tends to give away. And there are theoretical calculations supporting this argument. And under the argon beam, you can actually titrate. You can go on producing a series of non-cubic lattices. The lattice parameter goes on shifting, you can see that. This is also possible. Ultimately, it becomes FCC under excessive irradiation. So any argon plus ion coming with around 1000 eV kinetic energy can induce phase transformation back to its parent lattice. So it can be titrated against the energy imparted. So we could actually show it with calculation, such a possibility exists. Well, I have reached the conclusion now. I must tell you that for the first time, we have made microcrystals of non-cubic lattices of gold, which have very interesting physical and chemical properties as shown with lots of data here. And we also have done a bit of catalytic property. As you know, gold is catalytically neutral unless you make 1 nanometer gold dispersed on silica. Professor Yadav has worked on gold catalysis, and it's only in Professor Yadav's lab under such conditions where it's very tiny, it is catalytically active, but the moment it becomes bulk, all the catalysis is gone. But I must tell you that our gold, surprisingly, is catalytically active. I can show you that, but at a later time. So I must thank my students. It started with Gangaya. During his postdoc, unfortunate reasons, he passed away, very sad, but he had immensely contributed to beginning of this activity. Chetali Sahu, I already showed, she's working at Beamline at DESI. Suchitra also completed her PhD, and these are my collaborators, theory and experimental collaborators. And Professor Rao, he has been my mentor for decades. Thank you very much. Thank you for the opportunity.
Wonderful. Great. I forgot to mention that Professor G.U. Kulkarni was the president of Jawaharlal Nehru Center for Advanced Scientific Research, which is a DST lab. And so your topic was so interesting, you will have trouble at home. Your wife will ask you to give gold. And you said 100,111, the price of gold has gone beyond 1,100,000. So you better be prepared. Jokes apart, fantastic lecture, fundamental lecture. I liked it. We'll felicitate you. Of course, in the evening there is another program, but here.
Professor G.D. Yadav will felicitate Kulkarni sir with a memento and the compliments from ICS. Yes. Thank you so much, Professor G.D. Yadav sir, for chairing the session. Now we will, the actual time for lunch is 1:15. We are slightly behind the schedule by half an hour. So we will break for lunch now, and then we will assemble back here at 2:15 p.m. Lunch will be now for the delegates, VVIPs and staff members. Will be served at cafe in MCC MRF Innovation Park, and for the participants and the students, the lunch will be served in the canteen. We'll break for lunch, enjoy your meal, and return to the technical session at 2:15 p.m. here. Thank you.
Madam, for Yadav sir, all of these things are here. Yadav sir, felicitation, all memento.
Sir, Yadav sir.
Huh?
Yes, sir.
It is
here.
For me also it is here.
Yes,
keep
sir.
it here.
Yours is here. Said